This is the second video for the chapter related to elimination reactions in organic chemistry. And we're going to start looking at the stability of different types of alkenes. And remember, the alkenes, the ENE ending means that we have double bonds. And a lot of times when we're doing an elimination reaction, we have a leaving group leave. We have a acid pull off, or a base pull off hydrogen. And then we have the formation of the double bonds here. And then what we know is that this is similar to when we were looking at single bonds and looking at stability. When we have a trans isomer, and again, trans, we're looking at this double bond, and we're looking at the heavy molecular weight things off of going up or down across from this double bond. So this one goes up, and on the other carbon, it goes down. This is a trans double bond. And over here we have a cis double bond where it goes up on one side and up on the other side. So that's the cis bond. Now, it's interesting, this is more stable, but this is the type that we see more often in biological compounds and systems. This is the type of fat, the cis fat, that we typically see in our bodies. We're long chains of carbon. If we do, omega fats, for example, have this cis side. So the reason this happens instead of this one, even though it's more stable, is that we have enzymes that kind of force this shape on these long chains of carbon, and that's why we form the cis version instead of the trans. Another thing we know about the stability of double bonds and the areas around the double bonds, if we have a carbon-carbon, for example, this is the least stable type of double bond where it's just two carbons and then hydrogens on both sides of that double bond. But then when we move over and we add other R groups or other chains of carbon, if we do that, if we have additional, for example, this carbon's attached to three other carbons, we stabilize that double bond a little more. And as we continue to add different R groups and carbon chains alongside those, we get more and more stability as we continue to increase those other carbons. Because remember, we talked about this in the last chapter, where we can have those carbons can donate electrons. The sp3 hybridized carbons can donate electron density, and those areas are able to absorb that electron density a little bit more, so that helps with the stability of those groups. Part of the reason for that stability with the more substituted carbons attached to a double bond, remember, these double bonded carbons are sp2 hybridized, so they're 33%, right? So one of those three orbitals that are hybridized into the single orbital, these are going to be 33% S character. So S is more circular or rounded, spherical, and those pull in electron density towards its nucleus a little more. Here, sp3 hybridized is only 25%, so that's more elongated. It's able to donate that a little bit more. So just that description of why that is for those different carbons. So there's also, when we have, this is just showing you again some of that idea where we have that mono substituted, so just one of the carbons. So we have these two carbons on both sides of this double bond, just one substitution, which means just one of those groups. There's a hydrogen up here, there's two hydrogens here, so we just say mono substituted because just one carbon has a carbon on it. Here, this is a di-substituted, so we have a carbon up here, hydrogen down, again the hydrogen's just inferred. And then here's the cis di-substituted versus trans di-substituted. So as we move from left to right here, we have that increased stability. Okay, pause here. Now we've talked about this concept. Just kind of look through these two different options for A or B, and then write down which one you think is more stable. If you're not sure, go back and review the last few slides, and then that should help you decide which one of these two options are more stable. And this is another idea where you just want to rank the stability from the lowest to the highest, the least stable to the most stable. If you have four options, just rank those in that order. Again, if you're not sure, go back a few slides and watch that again, and then you should be able to answer this without a problem. All right, so now we're going to start talking about the mechanism. So what are we actually doing here in the E2 reaction? Remember, we need to identify where that leaving group is. So that's kind of the first step. And in this chapter, we're really looking at the halogens. And then this is going to be our alpha carbon, and then we have to identify beta carbon. So we have a beta here, a beta here, a beta here. And this one's kind of teed up for you already. We got the hydrogen available. So that is the hydrogen that we're going to pull off of that beta carbon. So here is our base. And remember that it's a base instead of a nucleophile in this instance, because we're going to attack a proton. And that's what we're going to do. We're going to attack that hydrogen. The hydrogen is going to leave the electrons behind, and it's going to place them in between the alpha and beta carbons that we've identified, and then the leaving group is going to leave. It's going to take the electrons with it. So that's what we have over here. This bromide ions formed. We have an H2O, a water molecule that was formed in that base attack reaction, and then we have our alkene that's formed afterwards with that elimination reaction. So this is an E2 type reaction. And we know, based on what we know about SN2, it's a similar idea. These things happen at the same time. So it's a constitutive reaction where we have all of this happening at the same time. Our base is going to make an intermediate with our proton. Our proton is going to start releasing those electrons to then form down here. So we have all of these things happening simultaneously. So this starts to pull off, and then and then this one leaves as well, and then we form the double bond. So this is the high energy transition state that we can see here. And remember this is also the E2 part, because it's an E2. That 2 refers to the things we're talking about, rate of reaction. So it's how fast this happens. So it's the rate of the reaction is a constant times the concentration of our leaving group compound times our base. So both of these things are involved, and that's why we get the 2 for that reaction. But there's only a single transition. And that should make sense, because this thing has to happen, and this thing has to be here. So these two things have to make contact with each other. And the concentrations of those, the more of the base you add, the faster the rate's going to go. The more of the leaving group compound, the faster the rate's going to go. So they're both involved in that transition state, and that's why they're both part of this rate constant. So what I would like you to do is I'd like you to use curved arrow formalism to show how the electrons move in this E2 mechanism. Now you might need to redraw this so that you include the hydrogens that are going to leave. So you're going to want to identify the alpha carbon, the beta carbons, the possible beta carbons, and then the protons that are associated with those beta carbons, because those are going to be attacked by the base. So do this, and then we'll come back, and if you're not sure, go back one slide and watch that video over again. That should help you understand what you should do. Make sure that you're practicing this. So practice is really important in organic chemistry. It really helps you. The more you do it, the better you get at it. So make sure you pause, take some time to do this, and then move forward. And we'll go through the answers later, but it's really good for you to try to do this on your own first. It helps you solve some of these harder problems. As we get into these different types of reactions, you'll notice probably that we're talking about a base versus a nucleophile. So that's the difference between an E2 and an SN2 type of reaction. So if we have a strong nucleophile, strong nucleophiles can be strong bases, and strong bases can be strong nucleophiles, but sometimes it's hard to get one to be one versus the other. And in this instance here, we have two different compounds that are typically used to kind of focus on the E2 mechanisms to really get us to what we want in terms of an elimination, if that's what we're looking for specifically. And the way that we do that is by making really big, bulky base compounds. So these are bases because we have a few different types of groups that are able to interact. We have a lot of different lone pairs of electrons and double bonds that actually can donate electron density to grab a proton. So here we have two compounds. We have diaza bicyclo 4.3.0 non-5-ene. So we don't have to memorize that, but basically we have the DBN. That's what we have, DBN here, and that's the same thing, but unidec 7-ene. So that's where we have these different dBn versus dBu. These shorthands are oftentimes used in organic places. They won't draw this compound out. They'll just have dBn, dBu, and you're supposed to know what that acronym stands for. I'm not going to ask you to memorize this, so don't worry about that. But just if you do see it, that's what this is referring to. So it's really acting. dBn, dBu are just strong bases that are used commonly used in E2 reactions. And here's an example looking at this. So the prostaglandins, that's the compound that's shown right here in the structure here, the long fatty tails, carboxylic acid on the end. We have this ring over here, and then we have a dBn base. And these are prostaglandins, and they're a group of physiologically active lipid compounds called icosanoids. And they have a lot of different diverse functions, typically hormone-like effects in animals. They're related to inflammatory responses, related to arachidonic acid. So there's a lot of functional use for these. And you can almost imagine if you have a picture of this and cholesterol, if you can imagine some of these rings coming together and forming, they can be the basis for some of those different hormonal-like compounds. So they have a similar hormonal shape, which gives them an effect. So here we can see we actually have the double bond is actually going to be involved in grabbing that proton, and then we have the leaving group leave, and then so we form this new double bond compared to the left to the right. So this is a way that it's really difficult for this to act as a nucleophile because it's so big and bulky. It's hard to get to, this carbon, for example, to pop that bromine off and add on. So instead, it has access to this proton, and that's what it does, forms a double bond. The next step of this reaction, we have another step, and it's not necessarily important with regard to the elimination, but it's just the first part of that process for creating a prostaglandin compound. So just like with the SN1 and SN2 reactions, the leaving groups have the same type of stability. So the bigger the ion, the more stable it is. And that again has to do with the entropy of the system. We have that negative electron charge has more space to be in, and it's a more chaotic environment. So it increases entropy. So that's more probable, a probable state. So this bigger thing is a better leaving group because of that. And as we get smaller and smaller, we condense that negative charge, which is a less favorable environment for that electron. I've referenced the substitution reactions in this chapter a few times, or in this lecture already a few times. And what we do have to worry about here is if we have a strong nucleophile or potential base, and is that we have to look at how they might compete in this chemical reaction. So when we have an SN2 type reaction, we know that the primary carbons, those typically are more likely to undergo an SN2 reaction. But when we move over and have more substituted carbon here, it actually we increase the rate of the E2 reaction. Because remember, what we're actually doing, if this carbon here is our alpha carbon and we're attached to the leaving group compound, and then this is our beta, we can go here to alpha, and then we have a beta 1 and a beta 2, and then we have an alpha still and the beta 1, beta 2, beta 3. What is actually happening is that we increase our probabilities of finding a proton close by that we can attack and pull off our leaving group. So when we have this E2, there's an easier shot at finding a proton in one of these spots where there's more substituted carbon on the end. So it's actually easier to attack the hydrogen, and so we actually increase the rate of E2 competition when we go from a primary, secondary to a tertiary carbon system. The other thing that has to be considered is this shown here. It has to do with the stability of the double bond. Remember, that's what we talked about at the beginning of this video, is that we looked at differences in mono, di, tri substituted alkenes. And what happens if we have a carbon where this is the leaving group? We have the alpha carbon, and let me label this one. So alpha, and then this is the beta carbon. This is just so we have this carbon here, and then we have a carbon here and here as well, right? We're going to form the double bond between alpha and beta. And so this is just a mono-substituted compound because we just have this group off substituted on one side. So it's mono-substituted. This is going to be a less stable compound compared to something where we have a carbon here, here, and here. This is our alpha. This is going to be our beta. And then we form, right, so this is 1, 2. It's di-substituted. It's more stable. We've talked about that already. And so this makes it more likely that this is going to go through an E2 reaction versus an SN2 type of reaction. So this is really to compare these two different things. So as we go from a primary to a secondary to a tertiary, that changes how many protons are available for the base to attack, but it also influences at the end the stability of the double bond where that forms on our compound. So quinine, I believe I also already spoke about this in the first video of this chapter. We look at this compound, the synthesis of this using an E2 reaction. Again, this is an anti-malarial drug, also used in tonic water. And what's going to happen here is we have our leaving group here. So this is our alpha carbon. And then we are it's only attached to one other carbon. So that's the beta carbon. We have 2 protons here that are not being shown. What we have is our base here, strong base, because we have a full negative charge, that metal ion that's involved as well. So we're going to move that there and that there. So then we form this new double bond and then several steps to get to this wonky structure over here. But this is one of the first steps in that synthesis process. So just like in SN2 reactions, for E2 reactions, polar aprotic solvents actually increase the rate of the E2 reactions. So E2 rate increases. E2 rate decreases for protic solvents because we have this strong intermolecular force that prevents it from acting. So it prevents it from acting as a strong base. So it weakens our nucleophile or our base, right? So it does that for both of them. So just again, coming back to the solvents, if you see those, that can influence the rate at which these undergo the reaction. So I'd like you to pause here, read through this example. This is a new learning check, looking at an E2 reaction between these 2 reactants. And if you're not sure, this next slide, you can go, if you follow along with your slide details, you can kind of look at, okay, is this a first, second, what is happening here? What makes better chemical reactions? Or go back a slide to figure out if we change the base to a different thing. So work through this problem, answer the question, bring this back to class, and then we'll kind of start with these learning checks for this chapter. And one more thing that I'd like you to do as well, I'd like you to go through these 2 different slides as well. So ranking the alkyl halide in each group in order of increasing reactivity in an E2 reaction. So work through that problem. And finally, looking at tripling the various parts components of an E2 reaction. So work through those 3 problems, and again, you can follow along with the lecture slides, but you can pause at each of those pages. Bring those problems completed to class the next time we meet, and then we'll go through those answers, and I'll check to make sure that you work through those. So we'll start at the Zaitsev's rule next once we've gone through the learning check questions.